Part 1 proved something uncomfortable. 5 industries, 5 different engineering teams, 5 different funding streams, a combined market cap exceeding $12 trillion, and none of them operating anywhere near their theoretical performance ceiling. Not close. Not within a decade of close with current materials. Each sector is running headlong into a wall that its own engineers can describe precisely, can quantify in millivolts and degrees Celsius and terawatt hours, can reproduce in simulation, and cannot break through, because breaking through requires a material that, until very recently, could not be manufactured at the required scale or cost. The question Part 1 asked was, why is progress slower than the projections? Why do the roadmaps keep extending? Why does the next breakthrough keep moving to the right? The answer was heat. Not heat as a vague inconvenience. Heat as a specific, quantifiable, material-constrained ceiling that every one of these sectors is pressing against, and cannot break through with the materials currently deployed. The Cross-Sector Thermal Unification Thesis states this formally. The primary constraint on performance across these 5 sectors is not engineering creativity, not funding, not political will. It is the thermal conductivity limit of the substrate material currently deployed in each system. 5 ceilings, 5 industries, 1 constraint, 1 solution. Part 2 is the mechanism of the solution. The physics of why CVD diamond resolves each ceiling, the engineering pathway from lab to deployed hardware, and the timeline derived from published capital expenditures, technology readiness levels, and the cost curve that became real when Rice University announced scalable MPCVD deposition at commercially relevant wafer sizes in February 2026. The material did not change. The manufacturing did. In 1856, Henry Bessemer did not invent steel. Steel existed. What he invented was a process that made steel cheap enough to build railroads and skyscrapers. That is the Bessemer moment for carbon. And it happened in February 2026. Thermal conductivity is not about absorbing heat. It is about moving heat away from the source before it can accumulate to damaging levels. The unit, watts per meter per Kelvin. The higher the number, the faster thermal energy moves through the material, and the less it builds up at any single point. Stainless steel, 16 W/K. The structural material inside most electrolyzers and industrial reactors. Aluminum, 205 W/K. Standard for consumer electronics heat sinks. Copper, 400 W/K. The industrial baseline, the material engineers reach for first when the problem is heat. Silicon carbide, 490 W/K. The current leader in wide bandgap power electronics, being adopted in EV inverters and industrial power conversion precisely because of this number. Single crystal CVD diamond, 2200 W/K. 5.5 times better than copper, 15 times better than silicon, 4.5 times better than silicon carbide, which is already considered exceptional. This is not a marginal improvement. It is a category change, the same kind that separates vacuum tubes from transistors, that separates cast iron from Bessemer steel. The diamond chip does not reach the temperature at which it would slow itself down. The ceiling does not exist because the heat never accumulates to create it. The protection system never fires because there is nothing to protect against. What Rice University announced is polycrystalline CVD diamond, grown on standard silicon wafers using microwave plasma chemical vapor deposition at rates compatible with existing semiconductor fab infrastructure. Polycrystalline achieves 1,800–2,000 W/K, slightly below the single crystal theoretical maximum, but still 12 times better than silicon and 4 times better than copper, and manufacturable at scale on existing equipment lines at a cost that has been dropping 30 to 40% every 4 years. The physics has been known since the 1950s. The obstacle was never the material. It was making it cheaply enough to deploy at commercial volumes. That obstacle was removed in February 2026. The semiconductor industry adopts CVD diamond first. Not because the application is most urgent at a civilizational level, but because chip companies have the shortest qualification path, the highest margins to absorb early adoption costs, and the most direct financial incentive. sustained compute performance that buyers are already paying for and not receiving. A leading AI accelerator chip today, NVIDIA H100, AMD MI300X, Google TPU V5, dissipates between 700 and 760 watts under full load. At the current trajectory of 3 nanometer and 2 nanometer logic scaling, the next generation reaches 1,200–1,400 watts per chip by 2028. The chips get more capable. The heat output increases proportionally. The thermal management solution has to keep pace, or the performance gains on paper never materialize in the data center. 200 watts of compute capability, 53% delivered. The other 47% permanently withheld every second the chip runs at full load because the thermal management system cannot keep the die below the protection threshold. That 47% is the market. It exists today in every data center running AI training workloads, multiplied across every rack and every facility running globally. It represents billions of dollars of purchased but not received compute performance every year, not a future market, an existing gap between the spec sheet and the delivered reality. One component change: the heat spreader, a flat plate between the chip die and the cooling system, representing 2 to 3% of total chip cost. That plate determines whether 47% of the chip's capability is available or not. Nothing else changes. Same chip, same rack, same cooling system, same data center, different plate. $280 billion of AI infrastructure spending projected for 2027. Every dollar buys compute performance. A $300–400 per chip component change that recovers 47% of sustained performance is not a cost barrier in a $30,000 AI accelerator. It is the most straightforward value proposition in the history of premium component pricing. Element 6 and Sumitomo Electric already produce CVD diamond heat spreaders commercially for high-power RF transistors in 5G base station infrastructure and military radar systems. The qualification process, the bonding chemistry, the manufacturing integration. These are solved problems in niche applications today. The Rice announcement changes the cost curve for high-volume deployment. Qualifying a new thermal material in a production semiconductor line requires 18 to 24 months of JEDEC standard reliability testing. That clock started running at every major chip company simultaneously in February 2026. The grid's thermal ceiling is not in the transmission lines, though those have their own thermal limits. It is in the power electronics, the switching devices, inverters, and converters that condition and route electricity at every node between generation and consumption. Every large-scale solar installation interfaces with the grid through a DC to AC inverter. Every wind farm uses a back-to-back frequency converter. Every grid-scale battery storage system uses a bidirectional power converter. Every EV fast charging station uses a high-power rectifier and a DC to DC converter. The heart of every one of these systems is a semiconductor switching device, a transistor that turns current on and off between 10,000 and 100,000 times per second. Each switching event dissipates a fraction of the conducted energy as heat. At grid scale, that fraction becomes enormous. Gallium nitride is the next-generation switching material, faster, higher voltage, lower resistive loss than silicon or SiC. Already deployed in premium EV chargers and utility-scale solar installations. But GaN on silicon has a thermal mismatch that limits what the technology can fully achieve. GaN and silicon have different thermal expansion coefficients. GaN at 5.6 ppm degrees Celsius, silicon at 2.6 ppm degrees Celsius. Under thermal cycling, which happens every time a power system ramps up or down, that differential creates mechanical stress at the GaN-silicon interface. That stress limits power density and operating temperature. GaN on CVD diamond resolves both problems simultaneously. Diamond's 1.1 p/deg expansion coefficient is closer to GaN than silicon is, reducing interface stress. Diamond's thermal conductivity removes heat from the GaN active layer 12 times faster than silicon, dropping junction temperature from 165 degrees to under 80 degrees C at equivalent power density. Result: 3 to 4 times the power density of GaN on silicon at the same junction temperature. Same chip footprint, same cooling system, 4 times more power throughput per unit area. 1.9 percentage points of efficiency improvement sounds like a rounding error. It is not. The U.S. grid converts approximately 4,000 terawatt-hours annually through power electronics. 1.9% of that volume is 76 terawatt-hours per year, electricity that is currently being converted to waste heat in inverters and converters across the grid, and that stops being waste when GaN on diamond becomes the standard switching substrate. The equivalent of powering 7 million American homes for a year. Not from new generation, not from new transmission. From one material change in one component type, deployed at scale. The hydrogen unlock is the most counterintuitive of the 5. The problem is not that the electrolyzer runs too hot. The problem is that it cannot run hot enough. Electrolyzer efficiency improves with temperature, described precisely by the Nernst equation, which governs the thermodynamics of electrochemical reactions. Higher temperature reduces the minimum voltage required to drive the water-splitting reaction. Less voltage means less electrical energy consumed per kilogram of hydrogen produced. Since electricity represents 70 to 75% of the total cost of green hydrogen production, operating temperature is the single most powerful lever available for driving costs down. And it is a lever that current membrane technology cannot pull. The Nafion membrane is why that lever is locked. Nafion, a perfluorosulfonic acid ionomer developed by DuPont in the 1960s, allows protons to migrate from anode to cathode while blocking both electron flow and gas crossover. It has excellent proton conductivity at low temperatures, and it degrades irreversibly above 80 degrees C. The research community has been working on higher temperature membrane alternatives for 20 years. Polybenzimidazole membranes, sulfonated hydrocarbon ionomers, phosphoric acid-doped variants. None has displaced Nafion in production electrolyzers at scale. Diamond enters through the electrode, not the membrane. Boron-doped diamond anodes have the widest electrochemical window of any known electrode material. 3.5 volts in aqueous solution before parasitic side reactions begin. Platinum, 1.6 volts. Iridium oxide, the current best practice anode material, approximately 1.8 volts. At 2 ACMTO2 operating current density, BDD anodes reduce the oxygen evolution overpotential by 180–220 millivolts versus iridium oxide. Overpotential is the voltage above the thermodynamic minimum required to drive the reaction at commercially useful rates. Reducing it by 200 millivolts means less electrical energy wasted per kilogram of hydrogen every hour the electrolyzer operates. 8 to 11% lower power consumption per kgH2 at 0.03 kW, 0.23 kg cost reduction per kilogram. The directed energy unlock is the fastest to reach production deployment. The defense acquisition community moves on published capability requirements, not commercial adoption timelines. When the requirement is written, the budget follows. When the budget follows, the qualification schedule follows. That sequence is faster and more predictable than any commercial market cycle. The published requirement is specific. 300 kilowatts of beam power on target, sustained for 60 continuous seconds against a supersonic maneuvering missile at 5 kilometers range. That is the performance threshold written into current U.S. Navy directed energy programs. Current production systems operate at 60 to 150 kilowatts. They sustain full power for 5 to 15 seconds before thermal management forces a mandatory cooldown. The gap between current performance and the stated requirement is not a gap in the laser physics. The fiber laser arrays that generate the beam are technically capable of sustained 300 kilowatt output today. The gap is in the optical chain that combines, conditions, and focuses that output. At 300 kilowatts, even 0.1% absorption in an optical element deposits 300 watts per second into a mirror the size of a dinner plate. Fused silica, the standard precision optical material, has a thermal conductivity of 1.4 W/Wm². It cannot remove that heat load without developing thermal gradients across the optical surface. Those gradients cause the optical path length to vary across the aperture. That variation distorts the wavefront. A distorted wavefront defocuses the beam. A defocused beam fails to achieve the power density required for target defeat at range. Simulation shows the fused silica mirror under 300 ws load. Strial ratio, the standard beam quality metric, drops 40% by second 15. A CVD diamond optical element under the same load maintains a strial ratio of 98.2% at second 60, providing a full engagement window with no degradation. CVD diamond optical elements have been in development at Fraunhofer, Element 6, and the U.S. Naval Research Laboratory for over a decade. The obstacle was aperture. 300 kL systems need windows in the 10 to 20 centimeter diameter range. Until 2026, diamond at that aperture required development-scale processing that put it beyond production program budgets. The same MPCVD deposition process that creates large-area semiconductor substrates creates large aperture optical elements. 1 February announcement: 2 simultaneous unlocks, one for chip companies, one for the Pentagon. The battery thermal unlock requires the least explanation of the 5, but it may affect the most people, most directly. Battery pack longevity is controlled by the hottest cell in the pack, not the average. Electrochemical degradation approximately doubles for every 10 degrees above 25 degrees. A cell reaching 50 degrees under DC fast charge degrades at 8 times the rate of a cell at 25 degrees, 8 times the degradation rate, every charging session, accumulating across hundreds of thousands of cycles over the vehicle's service life. Current liquid cooling leaves temperature differentials of 15 to 25 degrees Celsius across a large pack. The aluminum plates and thermal interface paste between cells and cooling structures cannot move heat fast enough to keep the pack isothermal under 250 kilowatt fast charge loads. CVD diamond thermal interface materials. Thin polycrystalline diamond films between cell surfaces and cooling structures reduce cell-to-cell temperature gradients by 60–70%. Hottest cells drop from 54 degrees to 35 degrees. Gradient drops from 23 degrees to 8 degrees. Degradation rate differential from 8x to under 1.56. Current premium EV, 500,000 km warranty at 1 DC fast charge per day. With CVD diamond TIM, 800,000 km projected, 60% life extension. No chemistry change, no cell redesign, no new battery management software. Here is what the unified timeline shows. By 2028, CVD diamond in commercial production across at least 3 sectors simultaneously. Semiconductor heat spreaders and data center AI chips. GaN on diamond in utility-scale power electronics. Diamond optical elements in naval-directed energy systems. 3 sectors, 1 material, 1 cost curve, all qualified from the same manufacturing announcement. By 2030, all 5 sectors have qualified deployments. BDD anodes operating in commercial hydrogen production. CVD diamond thermal interface materials in production EV battery packs. The aggregate market for CVD diamond thermal components exceeds $8 billion annually. By 2033, aggregate market across the 5 sectors exceeds $40 billion annually, larger than the entire global synthetic diamond market of 2020. Now I want to say something directly about what this thesis represents and why I am documenting it today, June 28, 2026. The Cross-Sector Thermal Unification Thesis is an original analytical framework, not a literature review, not a summary of existing analyst reports. It is the identification of a structural pattern, heat accumulation as the primary constraint across these 5 sectors simultaneously, and the derivation of a single material solution pathway from that pattern, anchored to a specific manufacturing milestone as the enabling event. The observation, stated as a unified thesis, applied to exactly these 5 sectors, connected to the Rice University February 2026 MPCVD announcement as the Bessemer equivalent unlock, is original work, conceived and documented on June 28, 2026 in this video, and its companion Part 1. I am not the person who discovered CVD diamond. I am not the person who designed the GaN diamond transistor, who developed the boron-doped diamond electrode, or who ran the Rice University experiments. Those are separate contributions by separate researchers whose published work is cited in the description. What I am documenting is the unification. The recognition that 5 separate engineering problems are one problem. The analytical framework that names the ceiling, identifies the material, maps the deployment pathway, and projects the timeline as a unified sequence, not 5 separate industry stories told by 5 separate analyst firms in 5 separate reports that never reference each other because no one has built the framework that connects them. The Bessemer moment is not one thing happening in one industry. It is 5 things that are actually one thing, wearing 5 different industry uniforms. The person who runs the experiment is doing essential work. The person who builds the framework that connects 5 experiments across 5 industries into one thesis is doing different essential work. My research into others' existing works led me here, as an observer, right at the time of the industry-altering cascade. Part 1 proved the ceiling, Part 2 mapped the unlock. What comes next is not another video, what comes next is the build. The record exists.